the K-type and the H-type instruments. And these instruments follow certain standardizations, whether they are K-type or H-type instruments. Have you ever given the H-type instruments? Have you ever given it a thought why they are called K-type instruments? See, K-type instruments, they are principally called because the endodontic instruments, the standard ones, they were initially made by Curve Manufacturing Company, by the Curve Manufacturing Company. It was in the year 1904 that the first commercial production of endodontic hand instruments started by Kerr Manufacturing Company. And that's why the term K-type came into use. We still use the term K-type file and K-type reamers. So there is a certain standardization of hand instruments. Standardization of hand instruments. A hand instrument, if you have ever seen, is something that looks like this. There are three principal parts of a hand instrument. One is the blade, that is the working part. Then is the shank, and then handle. Three principal parts are there for a hand instrument. And the total length of the instrument is designated as the length of the shank plus blade of the instrument. So whenever we designate length of a particular endodontic instrument, we exclude the handle and only the shank and the blade are counted for the length. '21, '25. And 31 millimeters. There is a slight technical snag. Sorry for the technical snag. I was talking about the instrument lengths. 21, 25, and 31 millimeters are the three principal length of the instruments which are available. So length consists of the length of the blade and the shank. Handle is excluded from the length. Another thing in the standardization is tip angle of the hand instrument. Tip angle is something, this angle, okay, angle of tip of the instrument. This angle is 75 degrees plus minus 15 degrees. According to ISO standards, the angle of tip of the hand instrument, whether it is K-type instrument or a H-type instrument, would be 75 degrees plus minus 15 degrees. Then other standardizations, if we talk about, is the blade length. One is length of the instrument, which consists of blade plus shank. Another is blade length. Blade length is fixed at 16 millimeters for all the type of instrument lengths, whether it is 21, 25, or 31 millimeters. Blade length is 16 millimeters only. Other things that we talk about are the size of the instrument, its color code, and diameter at tip of the instrument. Diameter at tip of the instrument. The diameter at tip of the instrument is designated as D0. I am again drawing the instrument structure for you. The diameter at tip of the instrument is called D0 and diameter at the end of the working blade is called D16. So this is the current ISO recommendation for the standardization of hand instruments used for endodontics. The diameter at tip of the instrument is called D0. Then the diameter at 1 millimeter from the tip would be D1. At 2 millimeter from the tip would be D2, and so on up to end of the working blade, that is 16 millimeter, it would be designated as D16. So this is one of the standardization. Whether the instrument is a K-type or a H-type instrument, it has to follow the ISO standardization of the diameter. And diameter at tip is called D0. At the end of the working blade is called D16. So if we look at the sizes of the instruments which are available, instruments have got three special sizes, that is number 6, number 8, and number 10. These are the three special sizes. Pink is the color code, gray is the color code for number 8, and purple is the color code for number 10 instrument. These are simple standardizations and straightforward questions come into NEET pre-PG. Like this year, if I talk about, they asked you about the color coding of the number 8 ISO instrument. What would be the answer? It would be gray in color. This was in NEET 2024 question. Okay. So it is important for you to remember the basics of the subject. I am talking about endodontic hand instrument standardization. Number 6, 8, and 10, they are special instruments with the respective color codes of pink, gray, and purple. Now, the third parameter that we have to look for is what does the size of the instrument indicate? The size of the instrument basically indicates diameter at tip of the instrument. And what do we call diameter at tip of the instrument? It is called as D0. So from size of the instrument, how do we calculate the D0? Simply divide the size by 100, you would get the D0 in millimeters. So if I talk about number 6 instrument, what would be the diameter tip? 0.06 millimeters, isn't it? Size divided by 100. So what does the size of an instrument indicates? It indicates diameter of that instrument at the tip, and that diameter we call D0. So for number 8, the diameter at the tip would be 0.08 millimeters. For number 10, the diameter at the tip of the instrument would be 0.10 millimeters. Then the standard endodontic instruments, apart from the special ones, start from size 15. There is an increment of 5, number 20, 25, number 30, 35, number 40. These are the 6 standard instruments with an increment of 5 each. And if I talk about the color coding, you have to remember 6 standard colors: white, yellow, red, blue, green, and black. Apart from the special instruments, these are the 6 standard colors and they repeat cyclically in the same order. Means after 40, the next instrument would be number 45 instrument. And what color it would have? Again, white. The sequence of 6 repeats cyclically. So number 45, then number 50, again it would be yellow. So what you have to remember, there are 6 standard colors: white, yellow, red, blue, green, and black, and they keep on repeating cyclically. Then there would be number 55 instrument, their number 60 instrument. So if I talk about the instrument sizes, which are the regular instruments, then from size number 15 to size number 60, the instrument diameter or the size increases by 5 each. 60 onwards, there's an increment of 10 each. So instead of 65, we have an instrument that is 70. Then we have an instrument 80, 90, and so on up to commercially available 140 to 150 size we have for instruments. This is the array of hand instruments available for root canal preparation. So these are some of the important aspects you have to remember. First thing, what does the size indicates? It indicates the diameter at tip, which we call D0. There is a certain color coding that is to be followed. White, yellow, and red, blue, green, and black. These are the 6 standard colors that will keep on repeating cyclically. Another important thing that you have to remember is from size 15 to size 60, there's an increment in size of 5. And from 60 till 140 to 150, there's an increment in size of 10. So increment of 10 each, increment of 5 each. Okay. And respective D0s can easily be calculated dividing the size by 100. And final standardization that we talk about is instrument taper. I am talking about standardization of hand endodontic instruments. Instrument taper. Instrument taper, if we again draw the diagram for the instrument, it is something like this: handle, shank, and the blade of the instrument. Okay. If we look at the blade of the instrument, the size indicates the diameter at the tip, that is D0. From D0 till D16, there is a progressive increase in diameter of the instrument. So D16 is the largest diameter at the end of the working blade. D0 is the smallest instrument diameter at the working end or the tip. So instruments are tapered. What taper? Standard instruments have got, standard ISO instruments have got a 2% or 2 degrees taper. Okay, 2% or 2 degrees taper is present. What does it mean? Percentage is out of 100. So it basically means 0.02 millimeter per millimeter. Each successive diameter is larger than the previous one by 0.02 millimeter. So diameter at the tip of the instrument is D0. What would be D1? It would be D0 plus 0.02 millimeters. Okay. Diameter at D3, 3 millimeters from the tip, would be D2 plus 0.02 millimeters. So each successive diameter is larger than the previous one by 0.02 millimeter. So this is the standard taper of the instrument, that is 2 degrees or 2% taper, that for each millimeter we go up, the diameter of the instrument increases by 0.02 millimeter. This is ISO standard taper. Instruments are available with numerous tapers, 2%, 4%, 6, 8, 10, 12% like this. But if I talk about hand instruments with ISO standard taper, what is the ISO standard taper? It is 2%. That is 0.02 millimeter per millimeter. These are the important points with regard to the standardization of hand instruments. Now we talk about K-type. K-type instruments. K-type hand instruments are principally of 2 types. One is a reamer, another is a file. A reamer and file. There are certain important differences between a K-type reamer and file, and always remember that they would follow the same ISO standards as we have already seen. Okay. A reamer is mostly made from a triangular blank of metal. From a stainless steel blank that is triangular in cross section, we twist it and we produce an instrument that is called ream. Files are usually made from a square blank of metal. A square blank of metal. Another difference between reamer and files is If we talk about cutting efficiency, the cutting efficiency of reamers is more, but that of files is less. If we talk about fracture resistance, whenever we use instruments inside the root canals, they are very narrow confines of the diameters, and the fracture resistance is an important for the instrument to prevent the instrument separation. So if we compare the fracture resistance between a file and a reamer, then a reamer has lower fracture resistance and a file has a greater fracture resistance. Another important difference between them is number of flutes per unit length. Flutes means number of twists which are present in the blade. We take a triangular blank of metal, we take a square blank of metal, we twist them. So number of twists which are present per unit length, okay, is called flutes, and number of flutes per unit length, they define the pitch of the instrument. How many flutes or twists are present per unit length is also called pitch of the instrument, distance between one blade and another pitch of the instrument. So number of flutes per unit length for the reamers is for less, and for the files it is more. Number of twists per unit length for the reamers is less. It is about 1.5 to 1 turn per millimeter. We give 1/2 to 1 turn per millimeter. For the files, the number of turns per millimeter is more, in the range of 1.5 to 2 turns per millimeter of length. So files are more dense instruments. Number of twists per unit length is more as compared to a reamer. This is the most technical and fundamental difference between a reamer and a file. I have listed several differences, but if you have to specifically point out the single most important difference between a reamer and a file, it would be the number of flutes per unit length. Okay, it is more for the files, less for the reamers. And motion of use. If we talk about the way in which the instruments are used, motion of use. For the reamer, the action is PRR, that is penetration into the root canal, clockwise rotation, and retraction. Penetration, rotation, and retraction. We would insert the instrument if this is the root canal. This is a reamer. It is inserted, that is penetration, clockwise rotation, and retraction. This is the sequence of using a reamer inside the root canal. For motion of use for files is basically a pulling and rasping motion, which is a linear motion. Pulling and rasping motion. Sometimes we also use watch winding motion for the files. These are the two principal motions that we use for the files. If this is the root canal and this is a file that is being inserted inside the root canal, pulling and rasping, linear motion against the wall of the root canal is called pulling and rasping. Watch winding, simply little clockwise, counterclockwise turn, watch winding motion. These are the two principal motions. So these are the fundamental differences between your K-type instruments. And what standardization do they follow? They follow the same ISO standardization with respect to the size, length, tip angle, color coding, taper, etc. that we have discussed previously. The second category of instruments are the H-type instruments. The word H basically indicates headstrong instruments. Headstrong. These H-type instruments, they are made from round and tapered blank of metal by process called multi-axis grinding. Multi-axis grinding. So you can see that there is a difference in the manufacturing of K-type and H-type instruments. K-type instruments, they are made by twisting either a triangular blank of metal or a square blank of metal. H-type instruments, they are made from a round and tapered blank of metal. Metal is most commonly stainless steel, and they are made by a multi-axis grinding. So what we get an instrument like this, which looks like a stack of cones. This is an H-type instrument. It would follow the same ISO standards that we have seen above. If I talk about instrument cross section, the cross section of the instrument, although it is made from a round and tapered stainless steel blank of metal, the cross section is not round because after multi-axis grinding, the cross section is teardrop. For the reamer, the cross section is same as the blank of metal that we use, that is triangular. For the K file, the cross section is same as the blank of metal that we use, that is square. But for H files, you have to remember we use a round stainless steel wire to make it through multi-axis grinding. But the cross section of the H file is H file cross section I'm talking about is teardrop in shape. It would be something like this because of multi-axis grinding. A modification of H file is S file, which is sometimes a double helical H file. An H file with more helix is called S file. Okay, it has a sigmoid cross section. It has got a sigmoid cross section, S shape in cross section. If we talk about cutting efficiency, then H file has got the maximum cutting efficiency, followed by definitely a K-type reamer and followed by K file. If we have to talk about three principal hand instruments, this is the sequence of the cutting efficiency. Then definitely what would be the sequence of fracture resistance? Reverse. The instrument that is least efficient in cutting would be most resistant to fracture. Reamer is intermediate to the two in both the properties, and H file is least resistant to fracture because its core diameter is very less. It is very prone to fracture if it is rotated inside the root canal. So if I talk about motion of use for H file, it is always linear. H file should not be rotated inside the root canal, and it cuts during retraction. You can look at the geometry again of the H file, which looks like a stack of cones. Okay. It looks like a stack of cones. So when it is inserted inside the root canal, first motion is insertion, second motion is retraction. And because of these sharp edges at the cone, it cuts the dentine during the retraction from the root canal, but the motion is always linear. Insertion, retraction. Okay. It cuts during retraction. Now, if we talk about certain file design characteristics or parameters, suppose this is an endodontic hand instrument or a file with flutes like this. Then This is the long axis of the instrument, and this is tangent to the blade. Tangent to the blade. This angle between long axis and the blade, this is called helical angle or cutting angle of the file. There are certain design characteristics of all these instruments. The angle between the long axis and the blade is called helical angle or cutting angle of the file. Okay. Cutting efficiency of a file is inversely proportional to its helical angle. Smaller the helical angle, greater would be the cutting efficiency of the file. Okay. Second characteristic is pitch. We already know number of twists per unit length for distance between two successive blade edges. This is called pitch of the instrument. So definitely pitch is high, greater for reamers because they are loose instruments, and it is less for the files. So this is the pitch of the instrument, helical angle or cutting angle, and pitch of the instruments. Another thing is the rake angle. Rake angle of the instrument. Rake angle is defined in cross section of the instrument. Okay. If I make an instrument cross section, which is a blade like this, then this is the radius of the instrument. Angle between the radial line and the front face, this is called rake angle. Angle between the radial line and the front face. If this is the direction of rotation of the instrument, what is this I have drawn? I have drawn cross section of one blade of an instrument. It is called rake angle between the rake face and the radial line. This angle is called rake angle. Rake angle is directly proportional to cutting efficiency. Higher the rake angle, greater would be the cutting efficiency of our instrument. And this rule is applicable not only to these endodontic hand instruments, but to the rotary instruments as well. Rake angle is directly proportional to cutting efficiency of the instrument. Okay. If we talk about H files, they have got a positive rake angle. K files, they have a negative rake angle. That's why the cutting efficiency of H files is more as compared to that of K files. These are the three principal type of hand instruments that we have seen. Now we talk about certain important rotary endodontic instruments. Rotary endodontic instruments. Rotary instruments, if we have to group them, they are sometimes called engine driven, okay, and powered instruments. Powered instruments. Engine driven instruments, they are low speed, mostly used with contra-angle handpieces, ledge type handpieces. Power driven, they are usually in the high speed. Engine driven low speed instruments, they include two type of instruments. One is GG drill. GG is the full form, that is Gates Glidden drill. Okay, and another type of engine driven low speed instruments are piezo reamers. They are piezo reamers. So two principal category of instruments which are rotary, means which are mechanized but used at low speed. So when I'm talking about low speed, what would be the RPM? They are usually used in the range of 750 to 1500 RPM, low speed instruments. GG drills, they have a design like this. There's a long and parallel metal shaft. At the end of that, there is a small flame-shaped head. There's a flame-shaped head. On the other hand, piezo reamers, they have got elongated parallel heads. The basic geometry remains the same, long and thin shaft, and they have a elongated head like this. Okay, it is an elongated head. So you can clearly see the difference in the geometry of the two engine-driven instruments. The flame-shaped head, they are called GG drills, and the elongated head are called piezo reamers. They are both low-speed engine-driven instruments, and they are available in 6 sizes: number 1, 2, 3, 4, 5, and 6. Both the instruments. Number 1 GG drill has a diameter of 0.5 millimeter, the tip diameter. Okay, definitely the working end is the flame-shaped head, and it has a diameter of 0.5 millimeter. On the other hand, piezo reamer number 1 has a head diameter of, sorry, not the tip, but the head diameter of 0.7 millimeters. Number 2, 0.7 millimeters for GG drills, 0.9 millimeters for piezo reamers, an increment of 0.2 millimeters. Number 3, 0.9 millimeters for GG drills and 1.1 millimeters for piezo reamers. Number 4, 1.1 millimeters for GG drills and 1.3 millimeters for piezo reamers. Number 5, 1.3 millimeters for GG drills and 1.5 millimeters for piezo reamers. And number 6, 1.5 millimeters for GG drills and 1.7 millimeters for piezo reamers. It is very simple to remember that each successive instrument has a head diameter larger by 0.2 millimeters from the previous instrument, and the beginning is 0.5 to 1.5 millimeter for GG drills and 0.7 to 1.7 millimeter for piezo reamers. If we talk about the uses of these two instruments, engine-driven instruments, the firstly, GG drills or the Gates Glidden drills, as the name indicates, they have small flame-shaped head is present. They are used for coronal flaring of root canals. Coronal flaring of the root canals, to enlarge the coronal portion of the root canals, GG drills are a good instruments because of their flame-shaped head. They are used to enlarge, but they should only be used in straight portion of the root canal. Straight portion of root canal. Only be used in the straight portion of the root canal. And the second use for the GG drills is for removal of lingual shoulder in anterior excess cavity preparations. In anterior excess cavity preparations for the removal of lingual shoulder. What is a lingual shoulder? If I talk about a maxillary central incisor in a buccolingual aspect and look at its anatomy, it has a root canal anatomy like this. There is an extension of dentine, okay, on the cervical lingual aspect of the tooth, which causes the root canal to bend at the cervical area. You can see there is a slight curvature in the root canal because of the dentine present in the cervical lingual area. And this prevents the straight line access of the instrument to the apical foramen. One of the principal goals of excess cavity preparation is that the instrument should have a straight line access to the first canal curvature or to the apical 1/3 of the root canal or apical forearm. So whenever we insert an instrument like GG drill, flame shaped instrument, and remove it outward, it straightens the root canal. That's why it helps in gaining an unimpeded access of the instrument to the apical 1/3 or apical forearm. So this lingual shoulder is basically an anatomical phenomena which is found in all anterior teeth, maxillary and mandibular, incisors and canines. And whenever we make access cavity preparations for the root canal in this group of teeth, we have to remove the lingual shoulder, and an instrument that can be used for this is GG drills. So these are the two important uses for GG drills. If we talk about piezo reamers, they have only one use, that is post space preparation. Simple to remember, P for piezo, P for post. To create space inside the root canal for insertion of post, we have to remove the gutta percha from the root canal. And what instrument can be used to remove the gutta percha safely without disturbing the apical seal? Piezo reamers. So only one use for piezo reamers and two important uses for GG drills. Both these are low speed engine driven instruments. The second category of instruments, mechanized instruments, which are predominantly used, are rotary nickel titanium instruments. Rotary nickel titanium instruments. The contemporary endodontics, the major chunk of instruments that we use for cleaning and shaping of the root canals, are the rotary nickel titanium instruments. This nickel titanium is basically an equiatomic alloy. Equiatomic alloy means equal number of the two elements are present of 55% by weight of nickel and 45% by weight of titanium. 55% and 45% by weight of these two respective elements, it results in equiatomic alloy that is called nickel titanium. This nickel titanium was first made by W.F. Buehler at Naval Ordnance Laboratory. Who was the first person to make this equiatomic alloy of nickel titanium? W.F. Buehler, Buehlar, at Naval Ordnance Laboratory, and the name of the first nickel titanium instrument was NiTi. Nickel titanium Naval Ordnance Laboratory. Okay, where the arms of the Navy were being made, Naval Ordnance Laboratory, military arm manufacturing facility. This nickel titanium is a unique alloy which is very much different from the conventional stainless steel that we use. The two important properties of nickel titanium. Nickel titanium. They are shape memory and superelasticity. Shape memory and superelasticity. These are the two unique properties of this nickel titanium. Okay, shape memory means a nickel titanium instrument manufactured in a particular shape, whether straight, curved, or any other shape, has a property of coming back to its shape whenever it is deformed. So it would fall back to its original shape whenever it is deformed. That's why it is very useful in curved root canals, because whenever the instrument gets curved inside the root canals, when we remove it, it would come back to its original position. Superelasticity means it is very flexible. Okay. Why these two properties are incorporated into it? Shape memory is principally because of phase of nickel titanium called Martensite phase. Martensite phase. And superelasticity is due to phase of nickel titanium called austenite phase. Austenite phase. So nickel titanium exists in different phases depending upon its stress and temperature. So martensite is basically a low temperature, high stress form, and austenite is a high temperature, low stress form. Whenever the instrument is heated and the stress on the instrument is reduced, it would exist in an austenite phase, which gives it a property of superelasticity. And whenever the instrument is stressed at low temperatures, it is under, suppose we are putting an instrument through a very tortuous or curved root canal, which phase, martensite phase, would be predominant, gives rise to the property of shape memory. Austenite phase gives rise to the property of superelasticity. Okay, these are the two principal phases of nickel titanium. Then there is an intermediate phase, which is also called R phase. Okay. Nickel titanium is a unique alloy of equal atomic concentration of 55% by weight of nickel and 45% by weight of titanium, and they would exist in different phases of forms depending upon the temperature and stress. So there is a continuous transformation from martensite to austenite and vice versa. And during this transformation from one phase to another, it undergoes an intermediate phase that is called R phase. R indicates rhombohedral. It is the crystal structure of this phase that is R phase. So martensite, austenite, and austenite to martensite transformations. Okay. These are the properties of super elasticity and shape memory. This is how nickel titanium is a unique alloy which exhibits these two properties and exists in different forms. And the process of transformation from one phase to another, depending upon temperature and stress, it is called twinning. So what is twinning? Twinning is the phase change in the nickel titanium alloy depending upon its stress and temperature. Now, this is the basic of nickel titanium metallurgy and the unique properties of this alloy that makes it different from stainless steel. Now we talk about generations of nickel titanium instruments. Generations of nickel titanium instruments. Basically, the same type of alloy is used to make the different nickel titanium instruments, but they are divided into generations. And this generation, the first one, they are called passive instruments. Passive nickel titanium instruments. In their design, there was a feature called radial length. These are passive nickel titanium instruments with radial lengths. If I make a cross section of first generation nickel titanium 5, it would be something like this. Okay. This is cross section of first generation of instrument. This is the axis or the center of the instrument. This is the blade of the instrument. And you can see the blade is not sharp, but it has got a flat end. And this flat end of the blade, this is called radial length. And this design characteristic of the first generation nickel titanium instruments makes them passive because they are not actively cutting the root canal. They simply auger because of the pressure from the instrument, and they are called radial landed instruments. Example of first generation nickel titanium instruments are Profile, GT files. GT stands for greater taper files, and light speed. Light speed. Three prominent examples of the first generation of nickel titanium instruments, which were passive, having radial lens. Now, what is passive? What is radial lens? I have told you. Okay. GT stands for greater taper files. Then comes the second generation of nickel titanium instruments. Second generation, they are called active instruments. Definitely, if they are active, there are no radial lines in their design. They have got sharp edged blades. So if I make cross section of an instrument, that is second generation, the blade edges would be sharp without radial lines. So they are active instruments. No radial lines are present. Right. Example of instruments which come under this category are pro taper. All of you must have heard the term pro taper, one of the most common and the significant instrument, most dominant instruments through which rotary endodontics started. Then there are M2 instruments. Hero, Race, etc. Numerous instruments are there, but what is the design characteristic? The blades would be sharp so that they actively engage and cut the dentine. So definitely radial lines or the platform like stoppers would not be present in them. Hero is an acronym for high elasticity in a rotation. Okay. Race is another term or acronym used for reamer with alternating cutting edges. Reamer with alternating cutting edges. So these are some of the examples of second generation of nickel titanium instruments. Then comes the third generation. Now, third generation instruments do not come into traditional martensite and austenite phases, but the instruments that have got special heat treated instruments. Special heat treated instruments. We give a special heat treatment to the nickel titanium alloys that increases its fracture resistance and also cutting efficiency. Increases its fracture resistance and cutting efficiency of the instrument. Special heat treated instruments. Okay. Example of instruments are high flex, CM. CM basically stands for controlled memory. Okay. High flex CM instruments. High flex EDM instruments. These are special heat treated instruments. Okay. Then comes the fourth generation of instruments. The fourth generation of nickel titanium instruments, they use a special motion. What is the conventional motion for any rotary endodontic instrument? Definitely rotary. They would rotate in a 360-degree circle. But fourth generation instrument, they are nickel titanium instruments, but they use a special motion. This special motion can be either reciprocation, okay, or it can be up and down motion. Reciprocation also called to and fro. to and fro motion. Means they would not rotate inside the root canal in 360 degrees, but they would reciprocate in clockwise, anti-clockwise manner. Okay. Prominent examples of reciprocating nickel titanium instruments are Wave 1 and Reciproc. What are these? These are the examples of instruments that work upon reciprocation. In up and down motion, the prominent example is SAF, that is self-adjusting file. Self-adjusting file. Self-adjusting file, it moves up and down in 0.4 millimeter amplitude. So basically what you have to understand in this nickel titanium instruments, they are classified into generations depend upon their principal characteristics. The first generation were the passive ones, second generation active ones, but both were using simple complete rotary motion. Third generation, a special heat treatment was given to the instrument so that to increase its fracture resistance and cutting efficiency. Fourth generation, alternate motion, either reciprocation or up and down. And finally, fifth generation instruments. They have offset design. These instruments have got an offset design. Offset design means the center of mass does not coincide with center of rotation. Normally, the instrument should rotate at the bang center of its blade, but here it has an offset design. So, instrument is represented something like this. Suppose this is cross section of an instrument, and this X represents the axis of instrument rotation. You can see that the axis of instrument rotation is eccentric, not in the center. So the center of mass of the instrument does not coincide with center of rotation. They have offset design. Example of instruments which come under offset design, fifth generation, are ProTaper Next, Revo S, and One Shape. Prominent examples of instruments with an offset design. What is the advantage of this offset design? The instrument has a self-centering capability inside the root canal. This offset design gives a self-centering capability to the instrument. Okay. These are the generations of your nickel titanium instruments depending upon their design characteristics. So prominent ones are the rotary definitely, but there are certain alternate motions also for these instruments. This ProTaper Next is sometimes also said to have a swaggering motion or a snake-like motion. Okay. When it rotates, it would have a snake-like movement inside the root canal, which is also called swaggering motion or snake-like motion, and helps in keeping it centered inside the root canal. If we have to compare the nickel titanium with the traditional stainless steel instruments, nickel titanium is an alloy. Two important characteristics are there we have seen. One is shape memory and superelasticity. And stainless steel, definitely the fracture resistance. The fracture resistance of nickel titanium is less and that of stainless steel is more. And that's why nickel titanium instruments have a high tendency of separation inside the root canals if they are not used properly. So, for safety of nickel titanium instruments inside the root canals, to prevent or minimize the separation of these instruments, there are certain things we have to remember. The most important factor is the clinician's skill. A person using a rotary nickel titanium instrument should be well versed with the endodontic skill. Secondly, is the root canal anatomy. Definitely, more tortuous the canal, more chances of separation of the root canal instrument. Third is location of tooth. Location of tooth. Anterior teeth are easily treated without the chances of instrument separation as compared to the posterior teeth. Approach is a problem. And the fourth factor is max Padden factor. Max Padden factor, which ensures the safety of nickel titanium instruments. What is max Padden factor? It is the ratio of torque needed to fracture upon working torque. Every instrument has a manufacturer recommended working torque, and every instrument has a torque, maximum torque, or the force that can be applied to the instrument for fracture. So the ratio of torque needed to the fracture upon working torque is called max Padden factor. So definitely greater the max Padden factor means we are using our instrument at a torque range which is much below the torque needed to fracture, increases the max Padden factor. So higher the max Padden factor that we are employing, greater would be the chances of safe instrument usage without separation. So these are some of the factors which influence the safety of the root canal instruments made of nickel titanium. Which is the most important factor? Clinicians' skill and the ability in handling such instruments. Now we have talked about nickel titanium instruments, the average speed range for rotary instruments, rotary nickel titanium instruments. Generally, there are specific recommendations for each instrument from the manufacturer, and it becomes very, very difficult to remember. That is not required for you for your NEET examinations. What you have to remember that rotary nickel titanium instruments are generally operated in the speed range of 150 to 300 RPM. An exception that you have to remember is, as the name indicates, light speed, which is a Group 1 first generation instrument, passive instrument, is used in the speed range of 1500 to 2000 RPM. Generally speaking, this is the speed range for nickel titanium rotary instruments. Specifically for the light speed, an exception which is there is in the range of 1500 to 2000 RPM. These are the basics of your endodontic hand and the rotary nickel titanium instruments. Thank you very much for being with me. With this, I'm closing this session. See you again next month with another interesting topic related to my subject. Till then, happy reading. Keep your dreams alive. Thank you very much. Good night, everyone.